In this video, we're going to look at directed graphs, also known as digraphs, and also the shortest path algorithms that you can use on weighted digraphs. So first we're going to define digraphs, then we're going to define walks and paths on digraphs, and then we're going to show how we can use an adjusted form of Dijkstra's algorithm and the improved Dijkstra's algorithm to find shortest paths between two vertices in a digraph. Alright, so I want you to think back to when we were studying relations. One of our models was actually called the directed graph model, and maybe at the time directed graph seemed like a weird phrase to use, but now it's going to hopefully make a little bit more sense. So when we had a relation R between sets A and B, if an element A was related to an element B, we expressed this relationship as A with an arrow pointing to B. And in fact, we can sort of do a more holistic look at what this meant in a relation. So if we had a relation where 1's related to 5, 2 to 8, 3 to 7, 1 to 2, and 3 to 5, here's what the directed graph version of the relation looks like. And we did this before. And you can see that 1 points to 5, 2 points to 8, 3 points to 7, 1 points to 2, and 3 points to 5. And one thing you might notice about this picture right now is it looks very much like a graph. In fact, the only difference is the edges in this directed graph are arrows instead of just lines or curves going from one vertex to another. Otherwise, it's exactly like a graph. And in fact, it is a type of graph. It's what's called a directed graph. So a directed graph, or a digraph, is a pair of, well, two sets. V is a set of vertices, A is a set of things called arcs that are pairs of the vertices, except, V can be any set, but the pairs have to be ordered pairs because we have to know which vertex is pointing at which other vertex. So if A, B is an ordered pair in A, we will visualize this as A pointing to B. And so each element of A is called an arc instead of an edge. So graphs and digraphs look very much the same. The only difference is the edges in the graphs are replaced with arrows. So a lot of the concepts we define for graphs have very similar concepts in digraphs. There are a lot of examples in the readings. I'm not going to go over all of those. I'm just going to go through a couple of things. I'm just going to look at walks and paths right now. So looking at walks and paths, they have very similar definitions as they did for graphs. So if you have a digraph G, a string of vertices V1, V2, etc. Are a walk if each consecutive pair of vertices has an arc between them in the right direction. So if we have a VI in that string of vertices, it has to point to VI plus 1. We can't have VI plus 1 pointing to VI. We have to travel along our walk in the same direction as the arrows. So we have V1 pointing to V2, V2 pointing to V3, all the way on down to Vn minus 1 pointing to Vn. And so those are all arcs. And so in a walk, just as in graphs we could have repeated vertices and repeated edges, in a walk we can have repeated vertices and repeated arcs, as long as we're going in the correct direction. And then a string of vertices is a path if it's a walk that has no repeated vertices. So just like we had for graphs. So as an example, here's a nice little digraph. And notice I'm putting the arrows in the middle of the edges rather than at the end so that they don't get bunched up against the vertices. But otherwise, they're just perfectly fine arcs. So here's a walk, A, C, B, A, F, D, H. And if you want to visualize that, we start at A. We travel along the arc in the correct direction to C, then we travel along to B, then we travel down to E again in the same direction as the arrow. We can go back to A, so we visited that one twice, go up to F, over to D, and over to H. And of course this is not a path because we visited the vertex A twice, and A is a repeated vertex. But if we do want a path, we can do G, E, C, F, B, D. And if you want to visualize that one, we start at G, we go to E, we go up to C, over to F, and down to B. Oh, and then one more, up to D. Now, just like in the old days when we had weighted graphs, we can have weighted digraphs. The only difference here is instead of putting weights on the edges, we put weights on the arcs. So a weighted digraph is a graph in which each arc is labeled with a real number. And if we're looking for things like shortest paths between vertices, we can use Dijkstra's algorithm. And improves Dijkstra's algorithm just like before. The only big difference is we got to make sure we're moving in the right direction when we make our labels. So if we want to find a shortest path between, say, A and all the other vertices, we're going to do it exactly like we did in Dijkstra's method. The only difference is we're going to treat the arcs as one-way roads. So if we start at A, of course, A to itself is distance 0. And we can travel from A to either F, C, or E because all the arrows are going in the right direction. The shortest one of those is going to be F. That's going to have a distance of 24. Now F can go to either D or C, and if we look at which one is going to give us the shortest one, it's going to be C, and it's actually going to be from A with a distance of 47. Now from C, we can go to either D, B, G, or E. Those are the directions that are going there. And the shortest one will give us C, vertex E from C, which has a distance of 70. And the next one from E is going to be, we can go directly from E to B to give us the shortest one there. The next one, we can go from B to G. That's going to give us the shortest one there. And if we can go from B to D to give us that shortest distance, and then we can go from D to H to give us that shortest distance. Again, it's just like we did for graphs. The only thing we have to be careful about is when we look from one vertex to the next, we got to make sure we're going in the right direction. All right, so now I think you're ready to work on the shortest path algorithms for digraphs. That's in the PDF file included with this video.